I'm going to talk about a tool I'm working on, the tool called Overload Inspector. To understand this, first we have to talk a bit about overloading in C++. We all know that it is a thing that functions can have the same name, and they must be called with different types. Usually the overloaded functions are constructors and operators, but of course this is not a rule, but only the custom. And overloaded functions are often used in metaprogramming too. And it is important to pick the right overload, to pick the overload which the programmer wanted to pick, because otherwise it can cause either bugs or bad performance, because we copied instead of moved the object, or we did implicit conversions which slowed the program down. And every time, if there are multiple possible overloads, the best of them will be called. But what does it mean that the best? Well, there are some rules for overloading in C++. I didn't list them all. These rules kind of are in priority. The most important one, which usually decides, is that the one with the is that that one will be called which has better conversions, meaning that there is at least one conversion, where the type we called the function is converting easier to f1's parameter than to f2's parameter. Note that if we have lots of like 10 parameters, and in 9 of them f1 is better, but in the 10th f2 is better, then the overloading will be ambiguous, and we will get a compile error. Another important rule is that templated functions are least likely to be picked than not templated ones. Not templated ones are prioritized, and there are additional rules for more. So if both of them are templated, then we will be interested in which template is more specialized or more constrained. And there are some edge cases for C++20's rewritten operators and deduction rights and surrogates, but I'm not going to talk about them. It sounds easy until we see some example where the result won't be what we think. This is a small example. We can usually the class we use isn't right up there, but in a header file. But I put it right about the code where we call the constructors. What will happen? Of course, the first is a new any made from an integer. Then we will move it. Then we will copy the B, the any which was in the B to the one in the C. But the fourth one, which looks really similar, constructs a new any with the templated constructor instead of copying it. And we can see that these two calls are almost the same, and the different overload was built. Well, that was because the parameter we gave to them was different. At the first one, we gave it a const any. Therefore, the template was deduced to const any reference, and in both the copy constructor and the templated constructor, the same conversion happened, so that couldn't decide. That rule didn't decide which was built. Therefore, the rule that was applied was that the template, the non-templated got priority over the templated one. However, in the second case, we had an any, not a const any. Therefore, the template was deduced to any reference instead of constant any reference, and it is easier to convert an any to an any reference than an any to a const any reference, and therefore we picked the templated constructor because of the first rule of overloading. Let me show you another example just to make sure that it isn't just one case where it can be confusing. So we have this code here with different declarations of the function foo. And we call it with an int pointer. So we expect it to print int pointer. Of course, usually functions don't print but do something, and then the debugging is way harder because we don't realize that what caused the bug. And it will print t star instead of int star. And why is it the case? Well, as we can see, the int pointer, when we declare the one with the int pointer, that's just a template specialization. And which template will be used from the specializations is only decided after overloading, after we picked which overload we use. And then, so we only compared to the first foo to the last, and therefore the last was chosen because t star is more specialized than t. However, if we flip the order and we declare the one with the t star at first, then we will the int star, then the one with int star will be a specialization of that, because that will be a better match when the compiler looks for which explicit template specialization belongs to which general template. So we will get a different behavior just because we flip the order of declarations. And it's extremely problematic because it's possible that we only exchange two header files, and the order which we included, the different files, change the program's behavior. As I mentioned, overloading is also often used in metaprogramming. and there it's not only important to pick the right overload, but also to pick the overload quickly, because our compile time is basically the equivalent to the runtime of the normal programming. And why we have good tools to profile why our program is slow for in runtime, we don't have such tools in compile time. Because we don't really have profilers and debuggers for compile time. So just so we can see that overloading is sometimes hard to get right, and if we mess it up, it can cause bugs. It usually metaprogramming, and unfortunately, there aren't many good tools which can help programmers to write code where they do the right overloading. That's the motivation for my tool, my overload inspector tool. This tool is a fork of the Clang compiler, so I could build it on a working infrastructure, and it knows all the language features. And it's guaranteed. It basically explains why we picked the overload and which one we picked. And it's guaranteed to always pick the same one as Clang because it's basically Clang. But unfortunately, this means that it's not portable to other compilers. So if someone uses GCC or MSVC, then they have to use Clang if they want to want the information from my tool. And I only have the information which already present at the overload resolution. My tool is basically I inserted tools to Clang, hooks to Clang to get the information about the overloading, and therefore, if my tool is disabled, it only causes minimal overhead.
Botond?
Yes?
Yeah, I was just wondering, what version of Clang is this currently based on?
It's last time rebased it at winter, so a few months old.
Okay, cool, thank you. So it should support like 23 or something. Like
it supports 23.
Cool, awesome, thank you.
So basically, I print a lot of information about the overloads. I optionally print YAML instead of something that is easy to read, because it's possible that someone wants to feed the distance output to some other program, for example, an IDE. And it not only says that it not only gives information about which overload was chosen, but also it measures the time it took to choose it. Well, at least the time it took for Clang to choose it. I know that it can differ in other compilers. It's basically customizable by giving different flags to it. And my long-term goal is to either make it into Clang or make it so it can be easily added to the latest Clang. Another tool related to this, basically that was my motivation, and I took some ideas from that. Is the tool called template. That kind of does the same thing, but for templates, not for overloads. So there is a lot of things which my tool prints if it's enabled. It lists all the candidates that were possible on display on the place record, and it puts them in different groups. Of course, it marks the best, but it also separates the viable ones from the non-viable ones. And it also marks that which ones were ambiguous, if any. And it gives information about what the templates were deduced to, and it basically prints a lot of information about the conversions, so at which place from which type we needed to do an implicit conversion to another type. And it gives reasons why a candidate were non-viable, and it can be very verbose by default, but it can be toned down, so it gives less information, because sometimes less information is more useful because it's more readable. Yes, I also print the time the overload took, and of course when I'm talking about a specific candidate, I mark them that where was it in the files. This is an example output of my tool. At the right side, we can see that what kind of program I was using it on. It's a really simple program. It says that the overload resulted successfully. It explains why the first overload were non-viable, because we couldn't convert a temporary double to a reference of a float. And basically it explains what happened in the other one, what conversions did we made, and things like that. This is another example. I will not spend a lot of time here. Here it says that it was ambiguous because in both of the cases we did a standard conversion. One of them was a floating to integer conversion, the other was a simple floating conversion, but according to the comparison of the conversions, they count as the same. So let's see what it does on a more complicated example. Here I run my tool on the code I first showed you. Especially I ran it so only the last one where the overload was not what we expected. I ran on that overload. So it says that we have the best candidate with the templated constructor, and it kind of explains that the other one, the copy constructor, was viable too, but we had a better conversion because the any to any is better than the any to const any. It's I know that it's a long output, but every part of it can be useful if can be used for sometimes. That's why we can tone down how much output we produce. In the second example, where I give explicitly I give a warning because an explicit specialization was ignored, where if that wasn't if that belonged to the other function, then that would have been chosen. No, I want to note that in neither of these examples, Clang or any other compilers, they gave no warnings. Well, here they do that. I use the in pointer uninitialized, but that has nothing to do with which function we will call. But my tool for these cases gives explicitly a warning that we ignore the specialization which would have been chosen. And it also explains why the first one, I mean the last one was better. And it's also, my tool can also be relevant nowadays because of the new feature, the new deducing this feature in C++23, because while it added no other hosts for overloading, they are just act like regular templated functions. They can behave weirdly if we overload functions with deducing this and without deducing this in the same class. So here is an example. We have two bar functions in this struct. One of them uses this new feature. The other one is don't. The first one has an integer parameter next to the object parameter. The second one has only a floating point parameter. And we can see that that in line 10 we get an ambiguity because the template is reduced to A, and we marked the second function as const. So and we have a non-const variable we call the function on. Therefore, the object parameters conversion is better for the first case, but for the second case, the float-to-float conversion, where we don't have to do anything, is better than the float-to-integer conversion. These are not outputs of my tool, but my tool outputs these comparisons about the conversions. The other overloads result as we expected them. So I will not go in details about them. If we don't put that const there, then it's kind of less surprising that at the first time we will call the bar function with a float, and all other times we will call that the bar function with int, because in the non-const, because in the second call we gave it an int, and later on we had a constant object, so bar wasn't even so the second overload wasn't even considered. Yes, so I would like to speak a little bit about the settings for my tool. we can do filtering which functions are we interested in by line or by function name. And there is a lot of things we can show or hide, like we can hide all the non-variable candidates or the information about the conversions and so on. We can switch between profiling, so measuring the overloading time, and the explanation where we explain why which candidates were chosen and why. There is more explanation on these in the GitHub repo. I would like to speak a bit about the timing or profiling, because overloading can take a long time, because every time we call an overloaded function, we have to look at each of its overload and decide if it's viable, and if there are multiple viable ones, then we need to compare them to each other. And if we declare n overloads for a function and then we call it m time, then it means n times m time. We need to evaluate n times m times how if something is viable, and after that we also need to do the comparisons and between them, and it can be a lot. Think about the output operator. We call that a lot of places, and we have overloads for a lot of times for that. That's why I want to measure the time each overload took. It can be used for metaprogramming if you want your code to compile faster. And it also can be used for library writers who want the users of their library to have smaller compile times. It's still very much in progress, therefore, so it's incomplete, but something I already did measure. For example, even the declarations of the candidates can affect the overloading time, the overloading took. Of course, I apply the same filters for this as for the explanations, so we can filter by line or by function name. It makes a summary, so instead of each, so it doesn't say at each call that how long that took, but it makes a summary for the file that which function, how many times we called it, and what was the time it took to resolve all the overloads. I believe that this is more important information than the information about the individual overloading time. I can be wrong. In this, maybe that would be more useful for me to print all the overloading times, but right now I print this way. So far I only use it on artificial examples and only in debug build, so I cannot, I didn't measure anything useful yet. Right now, all the times are, everywhere I measure whole time, and one thing I want to mention is that I measure separately that how long it took the children of an overload to resolve. These are, for example, the implicit conversions, because it is possible that multiple implicit conversions were possible at one place, and then we had to decide there which implicit conversion we use. It's for if you want to profile your metaprogram, it's simply just you have to run the tool and filter for the interesting functions and see which overload are too long. For library writers, you have to write a test file. You have to also write a test file in which you call your functions with realistic input types. But the usage is basically the same. So these two can help debugging of the code if it have problems with overloading. It can measure time of overloading took still in progress, but it can be helpful right now to it can be helpful in the state it is right now. And one more thing I would like to mention, I based it on Clang, and I already found two bugs where it resulted it printed not what I expected, and as it turned out, there was bugs in the compiler. Those bugs aren't there now. You can download the code from our GitHub, and any information about what would be useful or what should be the default way to print would be appreciated. Yes?
Have you thought, so I think that the profiling part of this is actually really cool. Have you thought about generalizing that out to like template instantiation as well? Because I'm thinking like from a library author perspective, if you have a lot of metaprogramming, like it could be really useful. Like I'm imagining like a flame graph or something that says like, you know, like we starting this instantiation, like we spent this much time here, you know, we spent this much time with the children over here. Like it would be really useful to be able to
I don't plan to expand it to templates because the template tool is already in existence, and that can do these things for templates.
Okay.
Yes?
If I write a template function and then there is some requires clause and etc., and then when I call it doesn't verify, does your tool tells that this guy was not didn't participate overload resolution?
Yes, it tells that it was not viable because the constraints weren't satisfied. Yes?
I have a specific question. So how I see it, you said like we have to write some sort of test file. So let's say I have like unit tests, yeah? But if I apply unit tests, I would get some sort of skewed results because I call my functions constantly like multiple times in the unit tests, and this would go into count. Some sort of filtering like in testing frameworks would be cool to not consider calls from particular file tests, for example, that it's my unit test. Because if I run the whole suite and I just say like count only function calls inside like the framework itself, which kind of, you know, call each other or do whatever, but not from my tests, this would, in my opinion, give like more realistic results, like what internally would be calling each other and where the times are coming from. And another like quick suggestion is not to print doubles, but you know, to put it into real like nanoseconds, microseconds, and so on.
That's not the. I know that printing doubles isn't the prettiest. I print how many times a function was called. So if a function took lots of time overall, but it was called a lot of times, then you can see that it's not that bad. You can the same way you can filter by line on the like I filtered on line here. I filtered so I only print the one on line 21. You can filter by line in profiling too. When you filter by line, you give intervals, line intervals in which you are interested in.
So I'm interested to filter by directory, saying like my source code is in src directory and my unit tests are in test directory, and everything what is in test should be included as calls, even if I would run my test suite, and then everything from src directory would be kind of counted, all the calls, but not from the test directory.
Right now, this tool only can do one file at a time.
Okay.
So right now, if you wanted to do things like run it on the whole project, you would have to run on each file and summarize the results.
Okay, got it.
But I will add the filter by file name or file path or something like
Cool,
that.
thank you.
I just wanted to comment that one of the things he said earlier is that you, instead of just printing stuff out, you could save the results as a YAML file. YAML files are really easy to write filters for.
Yeah, but they are sort of condensed. Or you mean the whole like output in YAML, and then I have to parse the output and do the work which kind of profiler does already.
Well, no, just you want to exclude a bunch of the results.
Yeah, but then I write my profiler basically. I mean, I understand it's easy in Python to do, and yeah.
Yeah.
Yes?
Maybe a solution for that using some kind of comment like Clang format off. You could have some comment like don't do in this file, things like that.
I mean, it could also be as simple as if you're collecting the YAML files afterwards, just have it do all of them, but just don't collect the ones for test afterwards. That would potentially be one way to do it as well. But yeah, so it handles requires clauses. If we have like old school like enable if constraints in place, how does it handle those?
It can handle those too. It registers if something was not viable and why was it not viable. I print the reason that the inner representation in Clang gave. So I print the same reason that was in Clang. I just print the enum of the reason. Yes?
Does this also include functions that might be found through ADL?
Yes, it includes all the functions that are there. All the functions Clang saw at that point, it includes.
What about functions that it saw but that are no longer picked up because the template doesn't allow them to be picked up?
Like disable it?
I think
No.
that's
Like the function was defined afterwards with a wanted overload, but the template was before it, so it's not allowed to be picked up only via ADL. But ADL may not step in. So will you print out those functions or not?
I only print out those functions which are found at the lookup.
Okay,
so
okay.
if it doesn't find it in the lookup,
okay.
I don't print it out.
Okay.
So regarding ADL, the question. So, okay, in profiler, let's say I have like shift operator, right?
Yes.
So shift something to the stream, and then I define my type in a particular namespace, and also define the shift operator there. How would the profiler show this information? Would it distinguish between two shifts, or would it just everything summarized into count like 10 now instead of 3?
Right now, it wouldn't be able to distinguish between these.
Yeah, I mean, I still can go into YAML and see probably the namespace from where the function comes from, right?
Unfortunately, the profiler doesn't save the information about at which namespace were in. So right now, it is not able to do that.
Okay.
Yes?
You mentioned plans to upstream this to Clang. Is that the entire tool? Is that just the hooks that you needed in order to sort of get your information? Both, or?
Well, I don't really know yet. It would be great if Clang, if it was part of Clang, but I don't think. I will see. I don't know yet. But I will try to keep up to date the Clang is based on. Does anyone have?
So I just wanted to say, like, if I have so many suggestions, it means that I'm excited about this tool. It's really cool one, and thank you for this.
Thank you.